A 0.25 kilogram model rocket is launched vertically with an engine that is ignited at time t equals 0. The engine provides an upward force of 10 newtons for 2 seconds. At the maximum height, the rocket deploys a parachute, then descends vertically to the ground at a constant speed of 15 meters per second. And we're going to assume the air resistance is negligible until the parachute deploys. In part A, we're going to start by drawing the free body diagrams for 3 different parts of the motion. So, part 1, while the engine is firing, so as soon as the engine has started firing, it's already left the ground, so it has no normal force on it. So it has the upward force of the engine. Like, we haven't really talked about this one in class that much, and it's okay if you just want to call it F. The technical name for it is the thrust force, so it's FTH, but just leaving it as F is fine. And then we have the downward force of gravity. Part 2, after the engine stops, but before the parachute is deployed, well, now it's just in a state of free fall. So it's still moving upward because it had quite a bit of speed at the end of the 2 seconds during which the rockets were firing, but now it's just slowing down due to the force of gravity. So that's it for part 2. And then after the parachute is deployed, well, it's still got the force of gravity on it, but now we also have the drag force from the parachute. You could also, on this last picture, if you want, label this one, if you want to treat the rocket separate from the parachute and just think of like the string of the parachute acting on the rocket, you could also label this an FT, and you would still get credit for that. Part B, determine the upward acceleration of the rocket during the first 2 seconds of flight. So in the first picture, we know that the rocket is accelerating in the upward direction because it's moving upward while speeding up. In the second picture, it's accelerating in the downward direction because it's moving upward while slowing down. And in the third case, there is zero acceleration because it is falling at a constant speed. So part B is asking about the first free body diagram. So we'll say that the net force in the y direction is equal to mass times acceleration, and the net force in the y direction is going to be the upward force minus the downward force equals ma, and you know everything in this equation. That should be a minus sign between those. The thrust force is given. That's the 10 newtons. The gravitational force is just m times g. You know the mass, so you can solve this for the acceleration, and you should get an answer of 30 meters per second squared. Once you have that acceleration, you can move on to part C, determine the speed of the rocket after those 2 seconds. Well, the rocket started from rest on the ground, so the initial velocity of the rocket was 0. The acceleration of the rocket you just solved for, that was the 30 meters per second squared. It says the time while it was accelerating at that rate was 2 seconds, and you want to solve for that final speed. So this is just basic kinematics, and you'll get an answer of 60 meters per second. In part D, determine the maximum height reached by the rocket. The tricky thing of this part is you have to realize that there is actually 2 separate heights involved. You have the first height you've got to solve for when the rocket is accelerating upward due to the engine that's firing, and then when it reaches that point, it doesn't just suddenly turn around and fall back to ground. It's got a pretty high speed at that point, so it's going to keep on going an additional height while slowing down until it reaches its maximum peak, where the velocity is equal to 0. So you need to solve for the delta y for this bottom part and the delta y for this next part, and then add those 2 delta y's together. And both can be done using kinematics. For the bottom part, we can basically use all of this same stuff right here and use that to solve for the delta y, and you should get a delta y of 60 meters. And then for the next part of the problem, the final velocity right here, which was the 60 meters per second, that becomes the initial velocity for this next part. So we can say the initial velocity for this next part of the problem is 60 meters per second. When it reaches its highest point, its velocity is 0. And because it's in a state of free fall, the acceleration is negative 10 meters per second squared. And from that data, you can get a delta y for the next part, which should come out to be, I think it was 180 meters. And then your total delta y, you just add those two numbers together. And for the part E, the total time the rocket spends in the air altogether, now it's a 3-part problem, because we have the initial part where the rocket's firing. Well, this part we already know the time because it was given as 2 seconds. We need to solve for the time for this part. That can be done using the same data that is over here. Just solve for time now. And you get a time of, I believe it was 6 seconds for that part. And now the third part of the problem is the rocket is falling back to Earth. So from its highest point, it's just going to come all the way back down, and that is falling at a constant speed. Now technically it is accelerating for that brief bit of time when it first reaches 0, but just to simplify the problem, because it reaches that terminal speed of 15 meters per second so quickly, we're just going to assume it has the speed of 15 meters per second all the way down. So you have to use the equation for constant speed, which remember is v is equal to delta x over t, or in this case we'll put delta y over t since it's vertical. And you know what the speed is. That was given as 15 meters per second. And you know the total delta y, that was the sum of these two numbers. So you can solve for the time, and for that part you should get a time of 16 seconds. So now you add the time for each of those 3 parts to get the total time. And for part F, where you're drawing the position and velocity versus time graphs, I'm not going to do these graphs for you. You need to figure this out, mostly by yourself at this point. You've already got, where like all the data points are. Like for example, we said that at t equals 2 seconds, right here, you know that the velocity is 60 meters per second. So on the velocity versus time graph, you can put a dot at 60 meters per second. We also know that at t equals 2 seconds, the position was 60 meters. So you can put a dot right there. And then remember, on the position versus time graph, the graph is concave up when the object is accelerating upward. Like in this first free body diagram, it's concave down when it's accelerating downward, like in the second diagram, and it's a straight line when it's not accelerating. And it's going to be a straight line going back down to 0, because the ground is where the position is equal to 0. The velocity graph should only be straight lines, either upward sloping, downward sloping, or horizontal. There should be no curved lines on the velocity graph.